Our next lesson is going to be on collisions, continuing in our unit in momentum. And in this lesson, we're going to look at energy conservation in collisions, and then we'll look at three types of collisions: elastic collisions, inelastic collisions, and totally inelastic collisions. So first, let's look at just how energy is conserved or not conserved in different types of collisions. So whenever we have objects that are in a closed system that collide, and so remember, a closed system is one where no energy is added to the system. It means if we have two objects that collide with one another, is that while those two objects may transfer energy from one to another, there's no additional energy that's added from outside the system, and likewise, there's no energy that leaves the system. When objects in a closed system collide, the total momentum is conserved. And so the energy, however, is usually not conserved. And so technically, then it may be a closed system or it may not for energy reasons here. But even if we do assume a completely closed system, is that what we end up finding out is that momentum is always conserved in a case of a collision with a closed system. Energy, however, is usually not conserved except in one case. And so let's talk about that case first. If the total kinetic energy of the system is the same both before and after the collision is called an elastic collision. The word elastic, usually think of it in terms of like certain types of clothing being stretchy. The key to the word elastic is it doesn't necessarily mean that it stretches, but rather that it returns back to the shape that it was originally. So an elastic waistband is one that when you stretch and let go returns back to its original size. An elastic collision is one in which the kinetic energy returns back to what it was to start with. So whatever kinetic energy it starts with, total is the kinetic energy that it ends with once the collision is over. And so that basically means that if you sum up the kinetic energies of each of the individual parts of the objects before the collision, and then collide the objects, and then sum up the kinetic energies of each of the objects after the collision, they would be the same total if you have an elastic collision. Now, in real life, that's very, very rare. Normally what's going to happen is going to be sort of our part two right here. If the total kinetic energy of the system is greater before the collision than after, that is, there's some kinetic energy that's lost in the collision is called an inelastic collision because we don't go back to the same conditions we were to start with. The energy that we started with is larger at the beginning than the energy that we end with whenever we sum up all of our kinetic energies. Other energies may still be around, the form of heat or other things like that, but kinetic energies, in this case, and just to clarify one other thing here, we're talking about basically a linear kinetic energy and kinetic energy due to motion in a direction. We're not worrying about any sort of rotational kinetic energy as an object spins. If it turns in from the linear kinetic energy in one direction into sort of a rotational kinetic energy, that would be considered to be an inelastic collision because of the fact that the kinetic energy that's linear, what we've talked about before, the 1/2 mv squared form right here, would not be conserved. But right now, this is all we're going to have to worry about is this. Next unit, we'll start talking about cases of rotational kinetic energy, and we'll pull that in. But for right now, all we're talking about is our 1/2 mv squared form. Now, next thing, a sort of a subset of inelastic collisions are what are called totally inelastic collisions. In a totally inelastic collision, the total kinetic energy of the system is greater before than after, just like an inelastic collision. But in a totally inelastic collision, the objects stick together after the collision. And so you have two objects that are basically moving, we'll say, towards, we'll say one is still going 0, another one is going towards it. They run into each other, and then once they run into each other, they've stuck together. And so in the case they've stuck together, maybe they're moving in some direction afterwards. That would be an example of a totally inelastic collision. Okay. Technically, you could also have a totally inelastic collision in the case of an object that starts off together and then breaks apart, like say an exploding shell. So we have some shell that's full of gunpowder that's moving in some direction, and then the shell explodes, which then shoots out fragments, every which way. And it turns out that, if you were to add up the momentum of your original shell right here and then the momentums of each of the individual ones right here, you'd find those are conserved. You get the same thing here. But because of the fact that this started off as one object here, they were sort of stuck together originally, and they ended up not stuck together afterwards. That's a sort of a different form of totally inelastic collision. But normally we're talking about totally inelastic, that they're not together to start with, but they are stuck together at the end. So let's take a look a little more in detail at some of these types of collisions. And so the first one that we're going to look at is going to be our elastic collision, where the kinetic energy is conserved. And so let me get this erased and we'll get there. All right, so in an elastic collision, what we said is that both momentum and kinetic energy are conserved. And so if we were to write this in equation form, we'd say looking at our momentum first. And so for our momentum right here, we'd say that the momentum of the first object before plus the momentum of the second object before plus the momentum of the third or the fourth or the fifth or however many objects that we have here would equal the momentum of the first object after plus the momentum of the second object after plus the third, fourth, fifth, sixth, however many momentums after. And so that's what happens in a normal collision. Momentum is conserved. But in an elastic collision, the kinetic energies are also conserved. And so the kinetic energy of the first object before plus the kinetic energy of the second object before plus the kinetic energy of the third, fourth, fifth, however many objects you have equals the kinetic energy of the first after plus the kinetic energy of the second after plus the kinetic energy of the third, fourth, fifth. Note this does not necessarily mean the kinetic energy before the collision of one object is equal to the kinetic energy of that same object afterwards. That kinetic energy may transform or may transfer from one object to another, but that the total, the net kinetic energy before and after the collision are the same. And so that's what happens in an elastic collision. This implies something. This implies that in the case of an elastic collision, there's no change in total kinetic energy. It means there is no energy whatsoever changed into other forms. Okay? So normally if you have a collision, you'd expect to say if I have, two balls rolling along the ground, two billiard balls that hit each other, you'll know they hit each other not just by seeing that their velocities change, but you'll also hear it. But sound is a form of energy. That energy was taken from the kinetic energy of the original two objects. And so if you have an elastic collision, then you would hear no sound. Because for there to be sound, then it had some energy, some kinetic energy would have had to been transformed into sound energy. And so that means no sound is produced in a collision. It means that your objects would not be dented or deformed. If you ever have seen a high-speed video of, say, a baseball hitting a bat, you can see that the baseball compresses pretty dramatically, and even the bat has some deformation of its shape. And so that type of thing takes energy. And so the process of doing that typically is one that would, except in the case wherever basically that they were perfectly elastic, that the ball popped back and didn't lose any energy in the process of doing that. Normally, that would be something that isn't going to happen in an elastic collision because the fact energy had to be taken away to do that. Typically, when two objects run into each other, it results in an increase in heat. If you take a hammer and hit a nail with it multiple times, the nail will eventually heat up because of the fact some of the kinetic energy is turning into heat energy. None of this can happen in a truly elastic collision. Because if it's a truly elastic collision, then, as he said, no energy whatsoever is changed into other forms. So, as you can sort of see, this is not likely to happen. In fact, true elastic collisions, typically the only case that you'll find them is if you have atoms that are in a gas that are colliding with one another. And we say atoms, we mean just atoms, things like monatomic gases like helium or neon or argon. If you had something like, say, water, what ends up happening is if you have your water molecule here, it's asymmetric. And so whenever those molecules hit each other, they tend to start rotating. And so when they tend to start rotating, well, that's some form of kinetic energy that's been transformed to another form. And so even water molecules in a gas, in water vapor form, would not be an elastic collision. You're pretty much only stuck with individual atoms in a gas. That's about the only real-world situation where you have a truly elastic collision. The scale that we live on that are very close to elastic collisions. Usually the classic example are two billiard balls hitting one another. Whenever that happens, because the fact the objects are very rigid, is that even though you can definitely hear them, is if you actually measure that, you'll find that you end up with something that's very, very close to an elastic collision. The amount of energy that's lost is very, very small, and so as a result is that oftentimes we will approximate certain types of collisions as they're elastic because of the fact that any energy that's lost is less than that which we can measure with the instruments that we have available. And so if we were doing a classroom type analysis of two billiard balls striking one another, then we very well might find that it's an elastic collision whenever we measure it to the degree that we can in the classroom. Even though if you really wanted to get super detailed, you'd probably figure out, no, this can't be a truly elastic collision because of the fact that we heard some sound, so therefore it lost some energy from that. But at least to the best of our measurements, we can approximate it as an elastic collision. And that's most of the time we use our elastic collision. What we'll use it for are these approximations. So if it's pretty rare to have elastic collisions, then what are most types of collisions that we're going to run into? Well, it turns out those are the inelastic collision, which is what we'll look at next. So in an inelastic collision, momentum is conserved the same way it is for elastic collisions, but some kinetic energy is lost. And so, we have, as we did before, our momentum equation that was right here. When we look at our kinetic energy equation, what we notice is the kinetic energy before of all the objects added together is going to be greater than the kinetic energy of all the objects summed together afterwards. We have lost energy in the collision, lost kinetic energy in the collision. And so, as I said, the final total kinetic energy is less than the original total because some of the original energy is transferred to other forms like sound or heat or rotation or something along those lines. Most collisions of macroscopic objects that we see are inelastic collisions. In fact, you could probably make a general statement that all collisions that you would see in your personal experience are truly, if you wanted to get down to the 50th decimal place, are going to be inelastic collisions. However, there is a subset of inelastic collisions we'll talk about next that you will see definitely, and so we have to take that into account as well. But so these inelastic collisions are more common. The reason why we don't just say, hey, let's just call everything that, is because this kinetic energy equation, because it has this greater than, means we can't solve it. And so if we have an equation, if we have a collision that is very close to an elastic collision, we oftentimes will use our elastic equation because of the fact that it gives us two equations that we can use to solve for the motion of the object. Whereas for an inelastic collision, you really just have the one. You have your momentum equation, the fact the momentum is conserved. This kinetic energy equation is honestly pretty useless in that case for an inelastic collision because all it just tells us is, hey, we started off with a greater kinetic energy than what we ended with. So we said that while, in truly, if we measured everything out, we'd find that the type of collision is always going to be an inelastic collision, but there is this subset of inelastic collisions that is called a totally inelastic collision. And so in a totally inelastic collision, the objects that hit stick together after the collision, okay? So momentum is conserved, same as it was before, but there's a little trick that we can use in this case. What we can do is, in a case of a totally inelastic collision, because they stick together, is we can treat the objects after the collision as a single object, okay? And so looking at our momentum equation down here, we said, okay, the momentum of the first object plus the momentum of the second object plus the momentum of the third, all the way out to however many objects we have here, added up in a totally inelastic collision would equal one object momentum. And this one object would be the sum of all of them. So, if I had a 1 kilogram and a 2 kilogram object that run into each other in a totally inelastic collision, then we would basically say, hey, let's just treat this as one 3 kilogram object that's going to be moving here. Because if they're stuck together, then they're going to be moving together as well. They'll have the same velocity. And so because they have the same velocity and we sort of put them together here, that's the reason why we can say, hey, let's treat this as just one object right here with one momentum. And that will make our solution a little bit easier sometimes. And so that's the reason why understanding if you have a totally inelastic collision is nice. Kinetic energy, as we said, works the same way as it does for an inelastic collision because a totally inelastic collision is a type of inelastic collision, which means the total kinetic energy before is greater than total kinetic energy afterwards. That is, some energy is lost, some kinetic energy is lost in the collision. So what we want to do, as we said, to treat the objects as a single object after the collision, we want to consider the combined object have the sum of the original object's masses and the velocity that they both will have because they'll have the same velocity because they're stuck together. Okay, so we just sum it up, and so if we had 5 objects that all somehow managed to collide and all stick together, then we would basically sum up all the masses of all 5 objects and use that as our mass afterwards times whatever velocity it has afterwards. So let's try some applications, see if we could use this to figure out what type of collision we have. So let's see. All right. So let's try an example here. Suppose a 15 kilogram block moving at 0.225 meters per second slides into a 30 kilogram block moving at 0.18 meters per second in the opposite direction. After the collision, the lighter block is knocked backwards at 0.315 meters per second. What type of collision is this? So let's sketch out our original situation. So we have a 15 kilogram block. So let's say here's our 15 kilogram block. The 15 kilogram block is moving at 0.225. And so let's say that it is going in this direction at 0.225 meters per second. Then we have our 30 kilogram block, which is, it says moving in the opposite direction. And so here is our 30 kilogram block moving in the opposite direction with a speed of 0.180, so 0.180. All right, and then it says that after the collision, and so this original setup is going to be our before, and then if we look at our after the collision situation here, that afterwards what's happening is that we have our 15 kilogram object, it says, is knocked backwards at 0.315, and so it was moving to the right, now it would be moving to the left in the way we set this up, and moving backwards at 0.315 meters per second. That's a 3. And then the other block, well, it doesn't tell us. And so our other block, which is still 30 kilograms, we don't know which direction it's going. We don't know its magnitude of speed either, so question mark on that one. And the question is, what type of collision is this? Well, you know, our first place to look probably would to say, hey, if this is a totally inelastic collision, they're stuck together. And so that's usually the first one you can identify if it's obvious here. But since we don't know how fast the 30 is going afterwards, we don't know. If the 30 ends up having a speed of 0.315 to the left, then we would say this is a totally inelastic because they're stuck together. If it's any other speed, then we say it's either going to be an elastic collision or an elastic collision or an inelastic collision. And so we've got to figure that out then by setting it into our kinetic energy equation to see, hey, is the total kinetic energy before and after the same, or are they different? And so that's going to be our general setup here. So first goal is, can we find the velocity of the 30 kilogram block afterwards? And so to do that, we know that in all three cases that the momentum is conserved. And so what we'll do is we'll set up our momentum equation and see what we can do with that. First, though, we need to figure out which positive is. Well, looking at the three situations we know, I'd say let's go ahead and say in the leftward direction is going to be positive because we have two boxes that are moving left. We only have one that's moving right. We don't know where the 30 is going to end up afterwards. So let's just call leftward positive. We could call rightward positive, but it's arbitrary, so we'll just call left. And as those were consistent, we're okay. So, taking a look at what we've got here, let's first look at the before situation. And so we know that the total momentum before should be the same as after. So the momentum of our first block, the 15 block beforehand, is going to be, we'll say it's going to be a mass of 15 kilograms times its velocity, which is going to be, in this case, negative. Oops, I'll put the negative sign in there. It's going to be negative 0.225. Has to be negative because of the fact that we said positive is to the left and it's moving to the right. And so that plus the momentum of the second block, which is going to be its mass, 30 times its velocity, which is 0.180. And so that should then equal our momentum afterwards. And so the momentum afterwards would be the 15 of the first block times its velocity, which is going to be 0.31, that's a 315, because it's moving in the positive direction, plus the momentum of the second block, which is going to be its mass, which is 30, times its velocity, which we don't know. So we'll just say 30v. So in solving this forward, let's go ahead and do some math on this. So 15 times 0.225, negative 0.225 is, let's see, negative 3.375. Plus 30 times 0.180 is 5.4. And then this should equal our momentum afterwards. So 15 times 0.315 is 4.725. 4.725 plus 30v, because we don't know that here. We'll just go ahead and subtract off our 4.725 from both sides. 4.725. So we'd say that we have negative 3.375 plus 5.4 minus 4.75. So we can do this to get negative 2.7. And so negative 2, that's a 2.7, should be equal to, on the other side, we have 30V right here. Just divide both sides by negative 2.7, negative 2.7. And so we get for this that the velocity of our second object right here should be, doing that math, equal to negative 0.09. So negative 0.09 meters per second. All right, so first thing, can we eliminate any of our types of collision right here? Well, considering the fact that our object is, we figured out, moving in a negative direction, which is this way, 0.09 meters per second. It's moving in opposite direction than the 15, so they're definitely not stuck together. And so that means we can eliminate totally inelastic. So it's either an elastic collision or a inelastic collision. And so to figure that out, we're going to have to put these in the kinetic energy equation. See, is the total kinetic energy before the collision and after the collision equal, or are they not? So let's find the kinetic energy of our first object, the 15. So for that guy, it's 1/2 mv squared would give us kinetic energy. So 1/2 times 15 kilograms times the velocity, which is 0.225 squared, plus the kinetic energy of our second object. So that'll be 1/2 m, which is 30 times the velocity squared, which is 0.180 squared. Note that I didn't have to put directions on those two because of the fact we're going to square them. And so it doesn't matter that the 0.225 is negative, because squaring negative 0.225 is the same as squaring positive 0.225. So then we'll go ahead and finish this out, and then equals the kinetic energy afterwards of our 15. So that would be 1/2 times 15 times its velocity, which is 0.31315 squared, plus our last object, the 30. So 1/2 times 30 times 0.09, I believe it was right, 0.09 squared. All right, so if this equation is true, then this would be an elastic collision. If it is false, if the before is greater than the after, then it would mean it's an inelastic collision. And for some reason, if it turns out that the after is bigger than the before, it means this is a physically impossible situation, or it means it's not a closed system. Somehow someone added energy to the system, which is normally not something we're going to run into here. So adding these up, let's see, 1/2 times 15 times 0.225 squared, let's see, is 0.3796. So 0.3796, 875 joules, plus 1/2 times 30 times 0.18 squared is 0.486, 0.486 joules, and then this should be equal to our afterwards, which is, let's see, 1/2 times 15 times 0.315 squared, which ends up being 0.744, 0.744, 1875, plus our 1/2 times 30 times 0.9 squared, which ends up being 0.1215. So let's go ahead and add these guys up. And so 0.3796875 plus 0.486 equals 0.8656875. So 0.8656875. And then on our after side, 0.7441875 plus 0.1215 equals, let's see, 0.865, that's a 5, 8656875. And so these two values, 8656875 and 8656875, are the same. Turns out these are equal right here, and so since the kinetic energy is the same after as is before, we would say that this is going to be an elastic collision. And so we know that based on our results, that these turned out to be the same down here. All right, so that would be an example of how you could use this to figure out what type of collision you have. So let's look at an example of how you might apply this to a situation that would be where you'd use this to solve a problem. Um, and so we'll look at a situation where a bullet is fired into a wax block. And so, this would be a stationary wax block to start with in this next problem that I'll pull up once I finish erasing here. And so it'll be a stationary wax block hanging from a string. And so we have a 2-gram bullet fired at 150 meters per second into a 2-kilogram wax block hanging by a string. The question is, how high does the wax block swing upward? Let's sort of think through what this would look like. So we start off with this little bullet that is it's a 2 grams, so that's going to be 0.002 kilograms. And our bullet is fired at a speed of 150 meters per second into, it says, a wax block that is hanging by a string. And so basically here's our situation. So here is our wax block. It's hanging by a string from something right here, hanging straight down. It's not moving here. We said this is going to be a 2-kilogram block right here. And so what's going to happen is the bullet's going to hit the block, and since it's wax, the bullet will embed into the block because it says it's fired into the wax block. It doesn't say the bullet goes through the block or blows out the side of the block. In this case, the situation that's meant here is that the bullet will stick in the block without having pieces of the block fly off. And so what's going to happen is when the bullet hits the block, it's going to cause the block to basically swing backwards. And so, so if we think about afterwards, the block as being up here because it swung backwards up to here due to the impact of the bullet, the momentum transfer. This is our situation. And the question is, how high does the wax block swing upward? And so really what we're asking here is we're saying, hey, when this goes up, it should go up by some height, and we want to figure out what that height is. And we should be able to do that because we know that height it will have once it reaches the highest point is going to be, it'll have potential energy. And so gravitational potential energy, and that gravitational potential energy comes from the kinetic energy that the combined block and bullet, because as we said, when this hits, we don't just have technically a block here, we also have a bullet that's now inside the block that's right there, it's stuck inside of it. That block bullet combined situation, it's going to have an energy right after it hits and right after it sticks. That kinetic energy is going to turn into gravitational potential as it swings upward because of the fact that there's no work that's being done here once the bullet has stuck into it other than gravity, and we'll have a gravitational potential energy term that'll take care of that. So let's see what we can do here. My first question is going to be, what type of collision is this? Well, we know that the bullet sticks into the block, and if it sticks into it, that means that we're talking about a totally inelastic collision. And so for a totally inelastic collision, then we know that the momentum of the first object plus the momentum of the second object beforehand must equal to the momentum of both afterwards. And so that's our situation here. So if we can use that to figure this out, then we should be able to do nicely on this. So let's figure out our bullet. Momentum of the bullet beforehand is going to be 150 meters per second is its velocity times its mass. It's mass times velocity, but it works both ways. So 150 is its velocity times its mass, which is 0.002 kilograms, because we've got to make sure we're in kilograms here. Plus the momentum of the block to start with. Well, to start with, the block's just hanging there. It has a velocity of 0, and so therefore a momentum of 0. And so we've got that. And so that should be equal to our momentum of the two afterwards. Well, afterwards, they're stuck together. And so since they're stuck together, we can treat them like one object. And we can treat them like one object that has a mass of 2 kilograms plus 0.002 kilograms. The mass of the block plus the mass of the bullet, because they're stuck together, we treat them like one object, times whatever velocity those have there, which we don't know, but we can figure out. So we just do 150 times 0.002, and that comes out to be 0.3 once we do it here. So we get 0.3 plus zeros gives us still 0.3, equals then 2.002 times V. So divide both sides by 2.002. Cancels over here, and so we get a velocity afterwards the bullet block combination that comes out to be 0.14985015. So 0.14985015. meters per second. All right, so we know how fast the bullet block combination has the instant after the bullet has stuck within the block. Now, that velocity means that this block now has some kinetic energy. And so that kinetic energy that it has is its entire original energy, and that kinetic energy is going to be turned into gravitational potential energy as the block goes upward. And once the block reaches its highest point, the block will stop, and so it has no kinetic energy, and so that means all of the energy is in the form of gravitational potential. So we need to figure out what kinetic energy does this block have to start with. Now, note that what we're saying here is we're talking about the kinetic energy going from kinetic to gravitational potential after the collision is over. And so you really don't have to worry about the fact of saying, hey, wait a minute, this is a totally inelastic collision. The energy is not conserved, because of the fact that we're not actually looking at energy until after the collision is finished. And so that's the way we sort of get around that issue that might otherwise cause us trouble. So let's take a look. So looking at our kinetic energy to start with, it'll be 1/2 mv squared. Well, afterwards, we have a combination, right? So it's 2.002 kilograms is going to be our mass times our velocity we just figured out, which is 0.14985015 squared, meters per second squared. All right, and so that should be our kinetic energy. And so then the kinetic energy here is, once we solve that out, equal to 0.0224, oops, sorry, that's a 7. Should be a 7. 2477522 joules. All right, so we figured out the kinetic energy it has. This is at this point right here, right after the bullet has connected into it, but it hasn't swung up any yet. And so this is going to turn into gravitational potential energy. And so gravitational potential energy, we know the equation for that, GPE, is equal to mgh. So we know the gravitational potential energy. That's going to be our 0.022477, 0.02477522 equals the mass, m, which is still 2.002, times g, which is 9.8, times the height, which we don't know in meters. So at this point, we should just be able to start doing some division here. Divide both sides by 2.002 and 9.8, right? 2.002 and 9.8. So the 9.8s cancel, the 2.002 cancel, and so when we do that, we're left just with a height of 0.001146 meters. So not very high. It's a very small bullet, even though it's moving pretty fast. And so this would end up being, what is that, 1.146 millimeters. So not very high at all. Significant figure-wise, let's see, that's 2 grams is spelled out, though 150 meters per second has 2 sig figs. The 2 kilogram wax is spelled out, and so the 2 spelled out ones have infinite significant figures. The only value we have here is the 150. All we're doing is multiplying and dividing this whole time, really. We have a little bit of addition, but that's not shouldn't cause much of a problem here. And so that gives us 2 sig figs, and so we end up with 1.1 millimeters is our final answer for the height that's millimeters, not meters. 1.1 millimeters is the height that the block rises once we've hit it with this bullet. And so that would be an example of how you'd work out a problem using totally inelastic collisions.